After 10, there is a general instruction for exercises 11 to 14. And what is that? For each of the differential equations in exercise 11 to 14, find a particular solution satisfying the given condition. A solution in which there is an arbitrary constant term C, that is called general solution. And if we find the value of arbitrary constant with the help of some initial value condition, then the solution is said to be a particular solution. So in sums 11 to 14, we need to find out particular solution. Let's start solution number 11. X cube plus x square plus x plus 1 dy upon dx is equal to 2x square plus x. And given initial value condition, y is equal to 1 when x is equal to 0. Transposing this bracket to right hand side together with dx, we may write this differential equation as dy is equal to 2x square plus x divided by x cube plus x square plus x plus 1 dx. So transposing this bracket, it goes in the denominator of right hand side and dx goes in the numerator. We have this equation. So obviously this is variable separable, so integrating both sides, we get integral 1 dy is equal to integral 2x square plus x upon x cube plus x square plus x plus 1 dx. So proceeding from this step, on the left hand side we get integral of 1 with respect to y. On the right hand side, we need to factorize the denominator in order to integrate the given expression. So 2x square plus x divided by, out of first two terms, x square is common. We get x plus 1 inside the bracket. And out of the second pair, we have only one common. So in the bracket, we have x plus 1 dx. That is equal to integral 2x square plus x divided by, now x plus 1 bracket is common, x plus 1. In the second bracket, we have x square plus 1 dx. And obviously this is the case of integration by partial fraction. So by partial fraction, we have to assume 2x square plus x divided by x plus 1, 2x square plus 1 is equal to a upon x plus 1 plus, this is quadratic expression, so we have to take bx plus c in the numerator for that. That is equal to, taking LCM x plus 1 x square plus 1, we get in the numerator a into x square plus 1 plus bx plus c x plus 1. Now, since the denominator on both sides are identical, so comparing the numerator of right hand side and left hand side, we have 2x square plus x is equal to a x square plus 1 plus bx plus c into x plus 1. Now proceeding from this step, putting x is equal to minus 1 over here in this equation, if x is equal to minus 1. Putting x is equal to minus 1 over here, on the left hand side we have 2 into minus 1 is square. Minus 1 is square becomes plus 1. So 2 into 1 is 2. And here we have minus 1 because it is plus x plus minus 1 is minus 1. On the right hand side, a into, here minus 1 square will be plus 1 and plus 1, that is 1 plus 1. And in the next term, x plus 1 becomes 0 when x is equal to minus 1, so it will make the whole term 0. So we have 2 minus 1 as 1 is equal to 1 plus 1, 2, a. So it implies that a is equal to 1 upon 2. Now if putting x is equal to 0 in this equation, putting x is equal to 0, we have on the left hand side both the terms will be 0. So we have 0 is equal to, on the right hand side 0 plus 1, 1 into a becomes a, and here b into 0 becomes 0 and only c is left over here. And here if you substitute 0, 0 plus 1, 1, 1 into c, c, that means only c is left. So we get 0 is equal to a plus c, implies that c is equal to minus a. So if a is equal to half, c will be minus half by substituting the value of a. So we get c is equal to minus half. Now if x is equal to 1, so on the left hand side we have 2 into 1 plus 1, that is 3. And on the right hand side we have 1 plus 1, 2, 2 into a, 2a. And here b into 1, b, b plus c, and that is 1 plus 1, 2. So we have b plus c into 2. So now putting the value of a and c, which we have already obtained, 3 is equal to 2 into half plus b we need to find out, and c we have minus half, so minus half into 2. So it implies that this 2 is cancelled by this 2. We have 3 is equal to 1. If we open up this bracket, 2 will multiply both the terms, so we have plus 2b, and minus half into 2 becomes minus 1. So this plus 1 and minus 1 are cancelled. We have 2b is equal to 3, or 3 is equal to 2b. So b is equal to 3 upon 2 from here. b is equal to 3 upon 2. So putting the values of a and b, c obtained in this equation, our initial assumption, that means in equation number 2, so we have 1 upon 2 upon x plus 1 plus 3 upon 2x minus 1 upon 2 divided by x square plus 1. Now splitting it up, we may write it as 1 upon 2 comes down to x plus 1. And if we split them up, because this is common denominator, x square plus 1, so it will divide both the terms separately. So we may write it as 3 upon 2 into x upon x square plus 1 minus 1 upon 2 x square plus 1, and let it be equation number 3. So this expression 2x square plus x upon x plus 1 x square plus 1 is equal to 1 upon 2x plus 1 plus 3 upon 2x upon x square plus 1 minus 1 upon 2x square plus 1. So now we have to replace this expression with the help of equation number 3 by this expression we get. So proceeding from this step, now we are going to replace this expression x square plus x upon x plus 1 x square plus 1 by this expression. So we get y is equal to integral square bracket 1 upon x plus 1 plus 3 upon 2 x upon x square plus 1 minus 1 upon 2 x square plus 1 square bracket closed. Now opening the bracket, we get half integral 1 upon x plus 1 dx plus 3 upon 2 integral x upon x square plus 1 dx minus 1 upon 2 integral 1 upon x square plus 1 dx. Multiply and divide by 2. So here we may write 2 in the numerator and we can multiply the denominator by 2. So we get here 4. Here we get 4 and here we get 2. Instead of 3 upon 2, outside we have written 3 upon 4 and inside 2x upon x square plus 1. Proceeding from this step, y is equal to first half integral of 1 upon x plus 1 is log mod x plus 1 plus 3 upon 4. Now see, 2x dx is the exact differential of x square plus 1, which is denominator of this expression. So if we assume x square plus 1 as u, 2x dx becomes du, and we have 1 upon u du, and integral of 1 upon u du will be log u, and after that if we replace u by the substitution x square plus 1 is equal to u, then we get log mod x square plus 1. So directly we may write it as log mod x square plus 1, and after that third term is minus half, and integral of 1 upon x square plus 1 is obviously tan inverse x, and then plus c. Let it be equation number 4. Because we need to find out the particular solution with the help of given initial value condition, we have to apply this initial value condition, that is that y is equal to 1 when x is equal to 0. So y is equal to 1 when x is equal to 0. Putting in this equation, so on the left hand side we get 1 is equal to half log, if we substitute x is equal to 0, so we get log 1 plus 3 upon 4 log, here we substitute x is equal to 0, we get log 1 again, and minus 1 upon 2 tan inverse 0 plus c. Now 1 is equal to, obviously when log 1 is equal to 0, these two terms become 0, and tan inverse 0 is also 0, so all these three terms become 0. So 0 plus 0 plus minus 0, only plus c is left, so we get 1 is equal to c, or c is equal to 1 ultimately. Now putting back this value in this equation, we get y is equal to half log mod x plus 1 plus 3 upon 4 log mod x square plus 1 minus 10 minus half tan inverse x, and c is 1, so plus 1. So this is the required particular solution of the given differential equation. Now 12th sum is differential equation x square minus 1 dy upon dx is equal to 1, and initial value condition is y is equal to 0 when x is equal to 2. So we need to find out this particular solution of this differential equation. So first we have to transpose this expression to right hand side. We get dy upon dx is equal to 1 upon x square minus 1. And then transposing dx to that side, we have dy is equal to 1 upon x square minus 1 dx. dy is equal to 1 upon x square minus 1 may be written as x plus 1 into x minus 1 dx. Now this is quite clear that it is a variable separable form of differential equation. So at this step, when we have separated both the variables, we have to integrate both sides. So integrating both sides, we get integral 1 dy is equal to integral 1 upon x plus 1 x minus 1 dx. Then obviously this is similar to the previous one, because this is the case of partial fraction, and now we have to break it up into 3 partial fraction with the help of partial fraction method. So I think you can do it well. So I am going to skip the rest of the part of the solution. So please try yourself, and if you have any problem, please write in my comment section and I will provide you the complete solution of this. Now 13th sum is cos dy upon dx is equal to a, where a belongs to set of real numbers, and the given initial value condition is y is equal to 1 when x is equal to 0. So given differential equation is cos dy upon dx is equal to a. Transposing cos to that side, it implies that dy upon dx is equal to cos inverse a. Transposing dx to that side, we get dy is equal to cos inverse a dx, and now it is variable separable form, so integrating both sides. On the left hand side we get integral 1 dy is equal to, on the right hand side, integral cos inverse a dx. So integral of 1 with respect to y is equal to. Now be very careful about this, because there is a chance of mistake over here. Cos inverse a is a constant expression because a is a constant. So cos inverse a is also considered to be constant. That should be taken out of the integral. So cos inverse a is taken out of the integration, and inside the integral 1 dx is left. So y is equal to cos inverse a plus c, constant of integration, With the help of initial value condition, we need to find out now the value of C for finding particular solution. So when y is equal to 1, when x is equal to, in this equation we have 1 is equal to 0 into cos inverse is 0 and plus C, or C is equal to 1. So now putting back this value of C in equation number 1, we get y is equal to x cos inverse A plus 1. This is the required solution of the given differential equation. Now 14th sum is dy upon dx is equal to y tan x. The given initial value condition is y is equal to 1, x is equal to 0. So now in this equation, transposing y to left hand side and dx to right hand side, we may write it as 1 over 10x 1 over y dy is equal to 10x dx. Integrating both sides, we get integral 1 over y dy is equal to integral 10x dx. Integral of 1 over y with respect to y is log y, and integral of 10x is log sec x plus log c. Constant of integration should also be taken in the form of log, because each and every term are in terms of log. Log y is equal to log sec x plus log c may be written as log c sec x. Now implies that y is equal to c sec x. Let it be equation number 1. Now for finding the value of c, we need to use initial value condition, which is y is equal to 1 when x is equal to 0. So putting in this, we have 1 is equal to c sec 0. As we know well, secant 0 is 1, so c is equal to 1. Putting this value back in equation number 1, we have y is equal to 1 into secant x, that is sec x. So y is equal to sec x, which is the required solution of the given differential equation. Question number 15, find the equation of a curve passing through the point 0, 0 and whose differential equation is y dash is equal to e raised to the power x sin x. Y dash is equal to e raised to the power x sin x. So y dash is equal to e raised to the power x sin x. This is given differential equation, and the curve whose equation is required that passes through 0, 0. So when x is equal to 0, y is equal to 0. So this is given initial value condition. Y dash, as we know well, is dy upon dx. So the equation is dy upon dx is e raised to the power x sin x. Now transposing dx to right hand side, we get dy is equal to e raised to the power x sin x dx. Quite clear, this is variable separable form, so integrating both sides, we get integral 1 dy is equal to integral e raised to the power x sin x dx. Integral of 1 with respect to y is y, so we have y is equal to integral. Obviously, e raised to power x sin x is the integrand which can be integrated with the help of integration by parts method. In that, the sequencing of the function is very important, which is taken according to the rule ILATE. I have explained in that dedicated video for integration by parts. You may check it out in the playlist class 12th maths on my channel. So the sequence should be taken as sin x as the first function and exponential function as the second function dx. So let it be equation number 2. Now y is equal to, this is first function, this is second function. So by integration by parts, first function is taken as it is, and then integral of the second, then minus integral as a whole of differential of first and integral of the second dx. Y is equal to, now again, e raised to the power x sin x. We may write this term as e raised to the power x sin x and minus, putting a square bracket, applying integration by parts. Again, this is first function and this is second function. So first function as it is, cos x integral of e raised to the power x is e raised to the power x minus integral as a whole differential of first. The differential of cos x is minus sin x. So that minus makes this minus plus sin x into e raised to the power x dx. Now bracket close. So e raised to the power x sin x minus, opening the bracket, we have minus e raised to the power x cos x and minus integral sin x into e raised to the power x dx plus c. Now as you see, integral sin x e raised to the power x dx is equal to y from equation number 2. So we may replace this expression by y. So we have y is equal to e raised to the power x sin x minus e raised to the power x cos x minus y. Now proceeding from this step, this minus y should be transposed to left hand side, so it becomes positive y. So we have y plus y on the left hand side, and on the right hand side we have only these two terms, out of which e raised to the power x is common. So e raised to the power x, within bracket we have sin x minus cos x, and a constant of integration should also be taken, that is c. That will be equation number 3. So y plus y 2y is equal to e raised to the power x sin x minus cos x. That will be equation number 3. So this is plus c as a constant of integration, and let it be equation number 3. So this is the equation of curve, but this is a particular solution for the given differential equation because it has an arbitrary constant c. So we need to find the value of c to find the required particular solution of the given differential equation. This curve passes through the point 0, 0. That means y is equal to 0 when x is equal to 0. So we have to substitute here y is equal to 0 and x is equal to 0 both. So 0 is equal to e raised to the power 0 sin 0 minus cos 0 plus c. 0 is equal to e raised to the power 0 is 1 and sin 0 is 0, in bracket 0 minus cos 0 is 1. So 1 plus c. So finally we have 0 is equal to minus 1 plus c, or c is equal to plus 1. So putting back the value of c in equation number 3, we get 2y is equal to e raised to the power x sin x minus cos x plus 1. So transposing this 2 to right hand side, it will divide both the terms. So we have y is equal to e raised to the power x upon 2 sin x minus cos x plus 1 upon 2. And this is the required particular solution for the given differential equation. Now the question number 16, for the differential equation x y dy upon dx is equal to x plus 2 into y plus 2. Find the solution curve passing through the point 1 comma minus 1. Also given that the curve passes through 1 comma minus 1. So now in this equation, transposing y plus 2 to left hand side and x dx to right hand side, we have y upon y plus 2 dy is equal to x plus 2 upon x dx. Now integrating both sides, we have integral y upon y plus 2 dy is equal to integral x plus 2 upon x dx. Now obviously y may be written as y plus 2 minus 2 in the numerator, y plus 2 in denominator as it is, dy is equal to. On the right hand side, we may split it up. X will divide x, we get 1 dx, and plus x will divide 2, then we get integral 2 upon x dx. So here we split it up, y plus 2 will be divided by y plus 2, we get 1 dy, then minus integral 2 upon y plus 2 is equal to integral 1 dx plus integral 2 upon x dx. So finally, integral of 1 with respect to y is y, minus this 2 is constant coefficient, should be taken out, and we get 2, and integral of 1 upon 1 y plus 2 with respect to y will be log mod y plus 2 is equal to integral of 1 with respect to x is x, and plus 2 is taken out as constant coefficient, and integral of 1 upon x dx will be log mod x. Now transposing this x to left hand side, we get y minus x, and this term minus 2 log y plus 2 to right hand side we have 2 log y plus 2 plus 2 log x. So we have y minus x is equal to twice 2 can be taken common out of these two terms. We have inside the bracket log mod x plus log mod y plus 2. Now we have to simplify this. Proceeding from this step, we have y minus x is equal to 2, and by logarithmic property, log mod x plus log mod y plus 2 may be written as log mod x y plus 2 plus c as a constant of integration. Let it be equation number 1. So now this is the equation of curve which passes through the point 1 comma minus 1 according to the given question. So we write since curve passes through 1 comma minus 1. So putting x is equal to 1 and y is equal to minus 1 in this equation, we have minus 1 is equal to 2 log modulus 1 minus 1 plus 2 plus c. So this is minus 2, and here we have 2 log minus 1 plus 2 becomes 1, so log 1 plus c. And as we know well, log 1 is 0, so this term becomes 0, and we have c is equal to minus 2. So putting this value of c in equation number 1, we have y minus x is equal to 2 log modulus x y plus 2 minus 2. Transposing this minus 2 to left hand side, we have y minus x plus 2 is equal to 2 log mod x y plus 2, and this is the required particular solution of the given differential equation. Though this answer may also be written in exponential form. Now problem number 17. Find the equation of a curve passing through the point 0 comma minus 2, given that at any point xy on the curve, the product of the slope of its tangent and y coordinate of the point is equal to the x coordinate of the point. Slope of tangent is always dy upon dx, that is slope of tangent at any point x comma y. Product of slope of tangent and y coordinate, that is dy upon dx into y, is equal to x coordinate of the point, that is x. So we may write it as y dy upon dx is equal to x. Transposing dx to this side, we get y dy is equal to x dx. Multiplying both sides by 2, we may write it as 2y dy is equal to 2x dx. Integrating both sides, we get y square. On the right hand side, we get x square the same way, plus c, constant of integration, and c is the constant of integration. Let it be equation number 1. This is the equation of curve. Now it is already given in the question that the curve passes through the point 0 comma minus 2. Since the curve passes through 0 comma minus 2, means this point will satisfy the equation of the curve. So putting x is equal to 0 and y is equal to minus 2 in this equation, we have minus 2 square is equal to 0 plus c, or c is equal to 4. Now putting back this value of c in equation number 1, we get y square is equal to x square plus 4, and this is the required equation of the curve. Now problem number 18. At any point x comma y of a curve, the slope of tangent is twice the slope of the line segment joining the point of contact to the point minus 4 comma minus 3. Now problem number 18, and this is at any point xy of a curve, slope of tangent is twice slope of the line segment joining the point of contact to the point minus 4 comma minus 3. Find the equation of the curve given that it passes through minus 2 comma 1. So the situation is, this is a curve and this is tangent at point x comma y. X comma y is the point of contact. So slope of the tangent at the point of contact dy upon dx is equal to twice, that is 2 multiplied by slope of the line segment joining the point of contact, that is x comma y, to minus 4 minus 3. Say this is the point minus 4 minus 3. So the line segment joining x comma y and point minus 4 comma minus 3 is this, and its slope is minus 3 upon x minus 4, that is y plus 3 upon x plus 4. Since slope of a line segment joining 2 points x1 y1 and x2 y2 is given by y2 minus y1 upon x2 minus x1. So using this formula we have found the slope of this line segment which is joining x comma y to minus 4 comma minus 3. So according to the language of the problem, the slope of the tangent at x comma y, which is denoted by dy upon dx, is equal to 2 times is equal to twice the slope of the line segment joining the point of contact and the point minus 4 minus 3, that we have found y plus 3 upon x plus 4. Y plus 3 upon x plus 4. And the curve passes through minus 2 comma 1. Say this is the point through which the curve is passing, and that is minus 2 comma 1. So this is the situation given in the language problem. Let's do it. Dy upon dx is equal to 2 into y plus 3 upon x plus 4. So transposing dx to right hand side and y plus 3 to left hand side, we get 1 upon y plus 3 dy is equal to 2 into 1 upon x plus 4 dx. Now integrating both sides, we get integral 1 upon y plus 3 dy is equal to 2 integral 1 upon x plus 4 dx. So log y plus 3 is equal to 2 log x plus 4 plus constant of integration should also be taken in terms of log. Now proceeding from this step, we may write it as log y plus 3 is equal to log. Using property of logarithm, this 2 can be written in the power of matrix x plus 4. So x plus 4 whole square plus log c. So now log y plus 3 is equal to log m plus log n is equal to log m into n. But this may be written as c x plus 4 whole square. Now eliminating log from both sides, we get y plus 3 is equal to c x plus 4 whole square. So this is the equation of the curve. Now as given, the curve passes through the point minus 2 comma 1. So this point must satisfy the equation of the curve. So putting y is equal to 1 and x is equal to minus 2 in this equation, we have 1 plus 3 is equal to c minus 2 plus 4 whole square. So 1 plus 3 is equal to 4 and is equal to c. Minus 2 plus 4 is 2. 2 square is 4 and 4 is cancelled by 4. So we have c is equal to 1. Putting this value in the equation number 1, we get the required equation of the curve, that is y plus 3 is equal to x plus 4 square. So this is the required equation of the curve. The volume of a spherical balloon being inflated changes at a constant rate, dv upon dt. Rate of change of volume of a spherical balloon is constant. Let it be k. Say, since balloon is spherical, so its volume is equal to 4 upon 3 pi r cube. So d upon dt of 4 upon 3 pi r cube is equal to k. Differentiating 4 upon 3 pi r cube with respect to t, we get 4 upon 3 pi 3r square dr upon dt is equal to k. So this 3 is cancelled by this 3, and we have only 4 pi r square dr upon dt is equal to k. Transposing dt to right hand side, we have 4 pi r square dr is equal to k. Now integrating both sides on the left hand side we have 4 pi r cube upon 3, and on the right hand side we have kt plus c as constant of integration. Let it be equation number 1. Next, it is given in the problem if initially its radius is 3 units. Initially means when t is equal to 0. Radius r is 3. Putting t is equal to 0 and r is equal to 3 in this equation, we have 4 pi upon 3 cube is equal to, and on the right hand side k into 0, that is 0 plus c. So 3 will divide 1 power from the numerator. We have 4 pi into 9 is equal to c, or c is equal to 36 pi. Putting this value back in equation number 1, we have 4 pi upon 3 r cube is equal to kt plus 36 pi. Let it be equation number 2. Next in the problem, it is given that after 3 seconds, it is 6 units. That is, when t is equal to 3 seconds, r is equal to 6 units. So putting in this equation, t is equal to 3 and r is equal to 6, we have 4 pi upon 3 into 6 cube is equal to k into 3, 3k plus 36 pi. So 4 pi upon 3 into 6 cube is 216, that is equal to 3k plus 36 pi. So 3 will divide 216, 3 sevens are 21 and 3 twos are 6, 72 times. Now multiply 72 and 4 pi, we have 4 twos are 8 and 4 sevens are 28. Pi is equal to 3k plus 36 pi. Dividing both sides by 3, we have 3 nines are 27 and 3 sixes are 18 pi. 96 pi is equal to k plus, dividing 36 by 3, we get 12 pi. Transposing 12 pi to this side, we get k is equal to 96 pi minus 12 pi. So we have 84 pi. Putting this value of k in equation number 2, 4 pi by 3 r cube is equal to 84 pi t plus 36 pi. Now transposing 4 pi by 3 to right hand side, it will become 3 upon 4 pi and it will multiply the whole right hand side. So we get r cube is equal to 3 upon 4 pi bracket 84 pi t plus 36 pi. So r cube is equal to, open the bracket, this will multiply both the terms. So 3 upon 4 pi multiplied by 84 pi t plus 3 upon 4 pi into 36 pi. 4 will cancel 84 21 time and pi is cancelled by pi. Here 4 will divide 36 9 time and pi is cancelled by pi. We have r cube is equal to 3 ones are 3, 3 twos are 6 t plus 3 nines are 27. So r is equal to 63t plus 27 whole raised to the power 1 upon 3. So this is the required radius after t seconds. Now problem number 20 is in a bank, principal increases continuously at the rate of R% per year. Find value of R if rupees 100 double itself in 10 years, given that log 2 base E is equal to 0.6931. So principal, let P be the principal. So principal increases continuously at the rate of R% per year. That is dP upon dt is equal to R% of P. It is dP upon dt is equal to R upon 100 multiplied by P. Now transposing P to left hand side and T to right hand side, we have 1 upon P dP is equal to R upon 100 dt. Let it be equation number 1. Now integrating both sides of equation number 1, we get integral 1 over P dP is equal to R upon 100 integral 1 dt. So integral of 1 upon P with respect to P is log P is equal to, and integral of 1 with respect to T is T plus C as the constant of integration. Let it be equation number 2. Now it is given that rupees 100 double itself in 10 years. So let initial principal is P naught, that is P is equal to P naught when T is equal to 0. So putting in this equation P is equal to P naught and T is equal to 0, we have log P naught is equal to 0 plus C, or C is equal to log P naught. Now putting the value of C as log P naught in equation number 2, we have log P is equal to RT upon 100 plus log P naught. Now proceeding from this step, transposing log P naught to left hand side, we have log P minus log P naught is equal to RT upon 100. Let it be equation number 2. Log m minus log n is equal to log m upon n. Using this property of logarithm, we may write it as log P upon P naught is equal to RT upon 100. Let it be equation number 2. Now it is given that rupees 100 doubles itself in 10 years. So P naught is equal to 100 and P becomes twice of P naught, that is 200 in time. T is equal to 10 years. Substituting P naught as 100 and P is equal to 200 and T is equal to 10 in equation number 2, we get log 200 upon 100 is equal to R into 10 upon 100. Yes, two zeros are cancelled by two zeros and we get log 2 is equal to, and here 1 0 is cancelled by 1 0, we get R upon 10. And as log 2 base is already given in the problem, that is given as 0.6931, so we may substitute the value of log 2 over here. We get 0.6931 is equal to R upon 10. So transposing 10 to this side, it will multiply 0.6931 and we get R is equal to 0.6931 multiplied by 10. So R is equal to 6.931 is the required rate of interest per annum. Now the problem number 21 is similar to 20th. So I am going to skip this one. You will have to try yourself. Now problem 22. In a culture, bacteria count is 1 lakh. The number is increased by 10% in 2 hours. In how many hours will the count reach 2 lakh? The rate of growth of bacteria is proportional to the number present. So let P be the population of bacteria at time t. So rate of growth of bacteria, that is dP upon dt, is proportional to the number present, that is p. It implies that dp upon dt is equal to kp, where k is constant of proportionality. Now transpose p to left hand side and dt to right hand side, we get dp upon p is equal to k dt. That will be equation number 1. Integrating both sides. Integral dp upon p is equal to k integral 1 dt. Integral of 1 upon p with respect to p will be log p is equal to k. Integral of 1 with respect to t will be t, integral 1 dt, and plus c, constant of integration, equation number 2. When the observation starts, that is at t is equal to 0, the population is found to be 1 lakh. So putting t is equal to 0 and p is equal to 1 lakh in this equation, in order to find the value of c, we get log 1 lakh is equal to 0 plus c, or c is equal to log 1 lakh. Be careful, log 1 lakh is not equal to 5 here because the base is e. Log 1 lakh will be 5 when base is 10. So let it be equation number 3. Now putting the value of c in equation number 2, we get log p is equal to kt plus log 1 lakh. Now log 1 lakh is transposed to left hand side, we get log p minus log 1 lakh is equal to kt. Log m minus log n is equal to log m into m upon n. So log p upon 1 lakh is equal to kt. Let it be equation number 4. Now it is given in the problem that the number is increased by 10% in 2 hours. So when t is equal to 2 hours, p is equal to 1 lakh plus 10% of 1 lakh. Count will be increased by 10%. So 1 lakh was already there, and after 2 hours 10% of 1 lakh will be increased. So 1 lakh plus 10% of 1 lakh. P is equal to 1 lakh plus 10,000. 10% of 1 lakh. P is equal to 1 lakh 10,000. So putting t is equal to 2 and p is equal to 1 lakh 10,000 in equation number 4, we get log 1 lakh 10,000 on 1 lakh is equal to k into 2. 4 zeros are cancelled by 4 zeros. We get log 11 upon 10 is equal to 2k, or k is equal to 1 upon 2 log 11 upon 10. Now from equation number 5, putting the value of k in equation number 4, we get log p upon 1 lakh is equal to half log 11 upon 10 into t. Now we need to find out that after how much time the count will reach 2 lakh. So that means t is required for p is equal to 2 lakhs. So putting p is equal to 2 lakh in this, we have log 2 lakh upon 1 lakh is equal to half log 11 upon 10 into t. On the left hand side we get log 2. The right hand side we have half log 11 upon 10 into t. So transposing this expression to left hand side, we get t is equal to 2 log 2 upon log 11 upon 10 hours. So this is the required solution of the given problem. when